So we spent quite a bit of time, about 9 videos, thinking about the equilibria associated with this thing. That's a monoprotic acid and its conjugate base. And we talked a little bit about if you have strong acids and they're in dilute solutions, that require systematic treatment because the concentration of that proton is comparable to the concentration of protons simply from the dissociation of water. We also said, well, if HA is weak, but it has a very low Ka value that's comparable to 10 to the minus 7, which is the equilibrium concentration of protons from dissociation of water, then that also requires systematic treatment. And we talked a lot about how to do that, systematic treatment. We talked about some shortcuts, when you would and when you wouldn't need to use these things. We then transitioned into, well, actually when we have a system where we have both HA and its conjugate base, A minus, well, that's what we call buffer. So we spent a little bit of time talking about buffers, what makes a good buffer, how you make a buffer, a few different examples. Then we finished with buffer capacity, which is this notion of, well, how much acid or base can you add to a buffer solution and resist this pH change. That was all with one proton. Of course, there are lots and lots and lots of acids out there, especially biologically relevant acids and bases, the things that make up our amino acids in our body, and macromolecules and oligomers that all have multiple protons. We call those things polyprotic acids. So polyprotic just means more than one. And so when we're thinking about polyprotic acids, one thing to consider here is, the nomenclature changes a little bit. And so if we've got, say, a triprotic acid, we're going to write that as H3A. That could have the possibility of popping off one of its protons. And what that's going to do is then liberate and produce its conjugate base, which is going to be H2A minus in this case, in this example. That's going to proceed through its first pKa or Ka1. Depending if we're log or not. That means that sets off some concentration of the H2A, which itself has its own equilibrium with its conjugate base. So it can pop off one of its protons and create HA2 minus, and that's going to be governed, or at least the ratio of those two species is going to be set by Ka2. And then finally, the last sort of form here would be for HA2 minus to pop off that last proton and produce the A3 minus moiety. That again is going to be governed by that final Ka3. So we've got just inside of one acid, H3A, we've got several different species that can be produced, right? Some amount of H2A will be produced. That tiny bit of H2A then enters into its own equilibrium, which will produce some amount of HA2 minus, which enters into its own equilibrium, which produces some amount of A3 minus. If all of these Kas are non-zero, which they are, there's no Ks that are zero, then what that means is even a minuscule amount of H3A in solution will trickle down some tiny bit of this A3 minus. In other words, when you're thinking about equilibria, there's no such thing as zero. Even the tiniest bit of H3A means that if these are non-zero numbers, there has to be some amount of its conjugate base in order to satisfy that expression, to make it non-zero, which means there will always be some amount of all of these species in solution, always. Anytime you have an equilibrium, which is always, you're always going to have both halves of the reaction. That's why when people talk about the reversibility of reactions, I find that to be a bit of a misleading term because it implies to you that if you have something that's irreversible, that you have zero of whatever is on the other side of the reaction. That's not true. It's never true. You always have some amount. Irreversibility just means you have a very large K that favors one side or the other. Even if you have a super large K, right, for, say, this reaction, HA goes to A minus over H plus, If this Ka is really, really big, it's still Ka is equal to A minus times H plus over HA. Even if Ka is 10 to the 9, it's a billion, which means that the concentration of these things is going to be a billion times that of HA. It's still not zero, ever. And why this becomes immensely important, not just for polyprotic acids and bases, but as we move forward, is sometimes when we're designing sensors and we're measuring things, that K may be 10 to the 34, huge, but we're still having impacts of whatever that trace amount of some species is in solution that has some important impacts. This is especially true in biological chemistry. Equilibria can lie immensely to one side or the other, be very large or extremely small, but that tiny trace of whatever that other species is in equilibrium is not zero, and often it's essential to a particular part of your biochemical reaction series. And so it's really important for us to transition in your thinking away from this sort of all or nothing equilibrium approach and really thinking about how the fact that everything is always in solution, always, and it's always in dynamic equilibrium. It doesn't mean you have lots of it, but it means it's there. It's not zero. So when we're thinking about the presence of all of these things in solution, we can think about this, as sort of what the dominant form of any species in a polyprotic acid base reaction series is going to be. And I think, just intuitively, you can look at that original sort of set of reactions here on a line, and that line can sort of simulate pH. And when pH is really low, what we have more dominantly, right? If pH is low, then that means we have most of the system in H3A form because we have lots of H+, which is driving the equilibrium to the left for all of these things. And at high pH, we're removing this proton, everything shifts to the right, and we start to move through dominant forms. So at very low pH, we have mostly H3A in solution, some amount of H2A in solution, less HA2-, and even less A3- in solution. But as we shift our pH higher and higher, at some point we move from H3A being dominant to H2A being dominant at a particular pH. If we keep shifting, then we move to a point where HA2- becomes dominant species in solution. And if we keep popping the pH up more and more, we reach a point where the fully deprotonated base, A3- is the dominant form. Again, doesn't mean that there's no H3A. It just means that the equilibrium of all of these reactions lie heavily to the right, but H3A is non-zero. It's still present in solution. So we can think about each one of these steps in the acid-base equilibrium. We can think about each step as from the perspective of our own Henderson-Hasselbalch expression. So, for example, if we just look at this light blue line and we're only considering the first reaction, the Henderson-Hasselbalch equation will be something like pH is equal to pKa1 associated with this first Ka plus log the base version over the acid version, right? And if we're thinking about what is dominant form of these things, we'll say that it's mostly in the form of H3A when the pH is low, but as the pH increases, at some point pH is equal to pKa1, at which point we have equal amounts of H2A and H3A. That's what this plot is showing here. So it's showing the predominant form as a function of the pK. So we have H3A, and then as we move higher and higher pH, at some point we hit pKa1, and that's when we have equal amounts of H3A and H2A. That's denoted by this vertical line because that's where we transition over, right? We go from H3A to H2A. So we keep increasing the pH. Now what happens is the H2A concentration goes up, H3A concentration, this goes up, this goes down, and our pH. So what we'll get to, what we aspire to in this series of videos, is to think about and have an intuition around what's in solution at any given moment in time. And by time I really mean pH. So at what pH do we have different species? And where we'll get to is thinking about these things called fractional composition diagrams and computing these things called alpha. And alpha really is just the fraction of 1 for each of these species. And so what I have here, and you don't need to fully understand this, but I think they're fairly intuitive, so we'll talk about them in great length later in other videos. We've got the composition, the fraction of whatever that species is here. This is just H2A. So the fraction that exists of that species as a function of pH. And this is a diprotic acid, so this isn't H3A like we just talked about. This is H2A, and so what we see is sort of at infinity low pHs. Then we have 100% of the fully protonated H2A. That's where the alpha 2A is at 1, and that's this curve here. So that means this blue molecule here, here are the two acidic protons. They are attached to the molecule at the low pH, which I think our intuition would tell us, right? Low pH means protonated molecules, as long as we're below the pKa's of each of those acidic protons. But as we start to move in the more positive direction, what we start to do is liberate one of those acidic protons, the first acidic proton, whatever that one is. I don't know in this case. It doesn't matter. It's a symmetric molecule. So what you start to see is as this starts to decrease, well then some other fraction has to make up for whatever else is in solution, and that's going to be that first proton being removed to make HA, and that's where you start to see the HA start to grow in. This starts to rise a little bit as this starts to go down, and of course they start to meet at the inflection right here. That intersection point is no coincidence. That is the pK. Why is that true? So at pKa1, that means that the fraction of H2A is equal to the fraction of HA minus, which makes total sense to us, right? Because based on the Henderson-Hasselbalch equation, which says pH equals pKa1 plus log HA minus over H2A, we know that when pH is equal to pKa, this whole thing goes to 0 because HA minus is equal to H2A, which is the same thing as saying that the fractions are the same. So this is more of a diagrammatic way to start to think about speciation. It's really convenient too, because you could just go in here and say, hey, how much of each of those species do I have at pH 3.5? So I go to 3.5 right here, I move up in space, and then I hit that point. That tells me that this fraction, I don't know what these units are, this is 0.1, that roughly 10% of all of the H2A is now in A2 minus form. I keep going up and I say, well, most of the H2A is gone, but there's still some of it. That's roughly, I don't know, 22% of the H2A. I keep going up to the blue line, and we're almost maxed out there. So we're at maybe 60, 70, 72, 73% is in the form of HA. And so that's a really, really quick way to differentiate. Of course, we could calculate any point on this line simply by using Henderson-Hasselbalch, and we will. We'll calculate these for sure. But this is sort of the roadmap that I want to get you to start thinking about. Of course, as we move past the first pK, then we start to grow in this next curve, which is the A2 minus. So that goes to HA2 minus plus H plus, which the equilibrium is set by the second pK. So we start to increase until we get to roughly halfway between the two pKa values. And then we start to descend again as we start to push this equilibrium further away. So we lose HA, we start to increase the amount of A2 minus until again we intersect at the second pK, and that's where alpha A2 minus is equal to alpha HA, which also means that the concentration of A2 minus is equal to the concentration of HA, which is, of course, when the pH is equal to pKa. 2. So this is a super helpful diagram. We could do this with triprotics. We can compute these in Hydra and Medusa very easily. And as you'll see as we get to complexation and we think about things like EDTA molecules that have 6 different, they're actually hexaprotic, we'll have much more complicated diagrams than this. So this is giving you a taste of what we're getting towards, but we're going to take a couple steps backward after this and talk about how do we get to those points. How do we think about computing the pH using more than one thing in this system? Because before this we've just used one Henderson-Hasselbalch, but that's not going to be sufficient here.